Hey everybody, this is going to be kind of a continuation of our geometric series. Now, when we were looking at geometric series in the previous video, we were looking at finding specific sums, right? Like the sum of the first 20 terms, the first 50 terms, whatever it might be. Okay, but what if we look at an infinite series, a sequence, that doesn't end, and then adding all of those terms together? What happens? Well, there's really two potential outcomes. It can either be convergent, meaning that the sum approaches a specific value, or it can be divergent, meaning it's going up into infinity somewhere where we can't actually calculate the value. Okay, so I'm going to show you an example of each, and then show you that if we do have a convergent geometric series, meaning it approaches a specific value, how it can actually calculate what that value will be. So if you look at the one in the red on the left side here, we have a half plus a fourth plus an eighth plus 1/16, and so on and so on and so on. Each time that fraction gets smaller, right? The ratio here would be a half. Well, if I add all of those values up, and you can see that I did the first 5 partial sums here. The sum goes from a half to 0.75, and it gets closer and closer and closer to 1. Every single time I add another term, this series is going to get closer and closer to 1, which seems strange, right? We're adding an infinite number of things together, and it's not going to infinity, it's going to 1. And any time you have a constant ratio that is less than 1, okay, like a half, a fourth, 3/8, something like that, you are going to have a convergent infinite geometric series. Now keep in mind, if the sequence you're working with is geometric in the first place, okay, anytime you are looking at a geometric series that is infinite, though, it's going to fall into one of these two categories. Convergent, meaning it approaches a specific value, or divergent. So let's look at divergent now, the one in blue. So here you can see we're doing a half plus 1, 2, 4, 8. Every single time the size of my number doubles. So we know just the sequence itself, right? Those numbers, the terms in my sequence, are getting bigger and bigger and bigger and bigger. So it only makes sense that if I then add those numbers that are continuously growing together, I'm not going to reach a specific value. That number is just going to climb further and further into infinity. Okay, it's going to approach infinity. And anytime you have a geometric series, an infinite geometric series, where your constant ratio is greater than 1, you will have a divergent series. It will not approach a specific value. It might go to positive infinity, negative infinity, or it'll just be impossible to calculate. Okay? So let's look at a specific example here. Now let's say we have an infinite geometric series, okay, and we find that it is convergent, meaning it approaches a specific value, okay? That means that we can use this formula that you see to actually calculate the value that it's approaching. So first thing that you need to check is, do I actually have a convergent series? And to tell, remember, you are looking to see if your ratio is less than 1. Well, I multiply by a fourth, a fourth, fourth. So yeah, our ratio is less than 1. That means that I will have a convergent geometric series. So now let's actually figure out what value it's converging to, what value it's approaching. So we need to know the first term, which is 1, and we need to know the ratio, which we just found. That's the only information I need to make this calculation. So the sum of this infinite series will be equal to my first term divided by 1 minus the ratio, okay? And if I do this calculation, I'm going to get 4/3. Now, what that means, again, remember, is that when we sum up an infinite number of terms, okay, the infinite number of terms within this geometric sequence, it is going to approach a specific value. That value in this case is going to be 4/3. Now, had I found that this series had a ratio of 2, I wouldn't have been able to do this, because then at that point, I have a divergent infinite series. I can't find a specific value that it's approaching. So this only works, one, if you have a geometric sequence, an infinite geometric sequence, and two, if that series, okay, the sum of the sequence, is convergent, meaning the ratio is less than 1. Okay, those things have to be in play in order for you to actually apply this formula here. So it's very specific. All right, that is it for this video. Let me know if you have any questions, and have a wonderful rest of your day.